So let's just go ahead and talk about it. It turns out that radicals are so high energy that once they react with something, they're going to keep trying to give away that high energy intermediate, okay? And what winds up happening is that it's like a game of hot potato, where no one wants to have the hot potato, so they keep passing it along, and it forms what's called a radical chain reaction, okay? Now, the chain reaction, it actually does mean that. It means that once you start it, it actually can't end until it's fully reacted, until you've fully reacted with all of your alkane. That is useful for us because, remember, alkanes aren't that great to begin with, so if we can react them completely, that's a useful reaction as an organic chemist. So let's go ahead and see how this works. Our first step is going to be the initiation step. The initiation step is where I get that first radical, because I can't play a game of hot potato without the hot potato itself. So I have to create that first radical. Now what you notice is that this mechanism is broken down into 3 different steps. And we're actually going to need to write all 3 of these steps. In fact, it's smart that you actually write the words if you do have to draw this mechanism for a test, that you write these 3 words: initiation, propagation, and termination. Okay? So let's look at the initiation step. And let's say that we're just using the easiest radical initiator, which is X2. Okay? And let's use X2 over heat. Okay? Now what I taught you guys is that in the initiation step, what we're going to wind up getting is electrons from 2 electrons, one on each side, jumping onto each X. So what I'm going to wind up getting is X radical plus X radical. Okay? That's the end of my initiation step. Really, all I need for the bare minimum of my initiation step to work, all I need is 1 radical. In this case, I have 2, so I'm great. Okay? Now that I have that radical in place, that radical is free to react with other molecules. Okay? And it turns out that it happens to react really well with alkanes. Now, for the sake of a really simple mechanism, let's just use the simplest alkane possible, which is methane. Okay? Methane just being a 1-carbon hydrocarbon. Okay? CH4. So now I've got CH4, and I'm reacting that with X radical. Okay? This X radical hates itself right now. It's super high energy, super unstable. It's saying, how can I get rid of this hot potato? How can I get rid of it? And then it sees all these electrons in the methane, and it's thinking, maybe I can take one of the electrons from one of those carbon-hydrogen bonds. And that's exactly what it does. So it turns out that radicals are going to react with hydrogens in alkanes. And the way we draw these arrows is, just so you know, radical reactions are always going to have 3 arrows. So I'm going to draw 1 fishhook into the middle of nowhere. Okay? Then I'm going to draw another fishhook from the CH bond meeting that one. Okay? What that's implying is that now there's going to be a new bond between the H and the X that's going to form from those 2 electrons. So that's looking great, but I still have 1 electron left over. Notice that the bond between the CH had 2 electrons. So where do you think that last electron goes? It goes onto the C. Okay? It goes onto the carbon backbone. So what that's going to do is it's going to give me a structure that now looks like this. C, H, 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 radical. Now notice that I'm drawing the geometry different, because now this would be trigonal planar, right? So you should draw it with like a triangle, and that would be plus HX. Making sense so far? So notice that the reason this is called a propagation step is because propagation means like I'm reproducing myself, propagating. And notice that the radical just reproduced itself. Now it kind of moved through my medium, and now I've got a radical on a new species. Okay? Well, it turns out that your propagation step isn't done yet, because you're not done with the propagation step until you fully reproduce yourself 100%. So what that means is not only do I need to have a radical at the end, I need to have the same exact radical that I started with. So if I start off with an X radical, I need to end off with an X radical. So what that means is we're actually just in the middle of our propagation step right now. What could we react my C radical with to generate that original X radical that we had at the beginning? Can you think of anything? It turns out the easiest thing to do is just to react it with another X diatomic halogen. Now, you might be wondering, well, Johnny, why isn't this already radicals? Because we just did that in the first step. We made it radicals. Well, it turns out that not all of the diatomic halogen is going to cleave at the same time. So some of it's going to do the initiation step, but some of it isn't going to be hit by enough light or enough heat to split up yet. So what that means is that the one I'm reacting with here hasn't cleaved yet. Okay, so this is one that's just waiting around for enough energy to finally do that homolytic cleavage. But wait, before the light can even get to it, another radical just did. So instead, we're going to propagate to the XX. And the way we draw these arrows is, once again, 3 arrows. So I'm going to take the radical, always starts it. I'm going to take the radical. I'm going to put that one out into the middle of nowhere, okay, between the C and the X. So then I'm going to take 1 electron from this bond and make it go there. This represents that now there's going to be a new bond of 2 electrons between the C and the X. But unfortunately, I've got 1 electron left over. I'm going to dump that one onto the X. So what I'm going to get at the end of this step is, now notice, C, H, 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 but now I've got an X. Okay? What do we call that functional group when we have a carbon and a halogen attached to each other? Alkyl halide. And notice that now I'm going to have X radical. So that's the end of my propagation step, because now I have the same exact radical that I started with. Okay? Notice that my propagation step just created a very useful byproduct, which is that it made an alkyl halide. Okay? Which, like I said, alkyl halides do a whole lot more stuff than alkanes do. So this is a very useful reaction for me as an organic chemist. Okay? So now we're going to do our termination step. Now, what is termination? Termination means that, okay, you're producing all these radicals. These radicals are spreading. Radical, radical, radical. You're generating all of them, okay? What happens in termination is that you finally have so many radicals that instead of propagating and forming new radicals, they're actually extinguishing each other faster than they can make new radicals, okay? Because think about it. If you have 2 radicals coming together, if they hit each other, what do you think is going to happen? Well, I've got 1 electron here, 1 electron here. They're going to form a new bond. So the termination phase is what happens when there's so many radicals that they actually bump into each other. They collide into each other more often than they collide into unreacted species. Okay? So in my termination phase, what I do is I look at all the different possibilities of radicals that could have collided. So the easiest radicals to think of that could have collided are just X plus X, right? Because these are being formed in high amounts. What happens if they hit each other? Well, I would just wind up getting the same thing all over again. I would do this, I would do that, and I would get XX. Okay, so that's one termination product. But there are actually some other termination products possible. Can you think of another one? Another one would be if I had an X radical and a CH3 radical, right? Okay, that would be like the radical that I had up here in black, where maybe instead of hitting an XX that wasn't reacted yet, maybe it reacts with a radical. Once again, I get my arrows. And what I get as a product here would be CH3X. Okay, so I get an alkyl halide. Okay? Can you guys think of any more combinations? There actually is one more, and that last one would be, well, what if I got CH3 radical plus CH3 radical? Okay? Now, this is tricky because now it looks like I'm going to get a completely different product. And it's true, what I would get now is actually ethane. CH3, CH3. Crazy, right? So now what I just did is I just made a larger hydrocarbon than before. Before I just started off with methane, and now I'm getting ethane as a product. Okay? Well, a few notes about these termination products. First of all, the first one is not going to really matter. Okay, so I'm just going to say, I don't know, I'm trying to think of like a symbol that I can use. But just like, let's say I have termination product 1, 2, and 3, right? Number 1 isn't really going to matter that much. And the reason is because after I make the X2, it can then just react with heat or light again and make radicals again. So really, this is a termination phase that happens and then it dissociates again. So you're not going to get a whole lot of X2 forming because the X2 keeps breaking up. Okay? So that's the first thing. So actually, X2 isn't going to form a whole lot. Now, your professor still probably wants to see that termination step, but just as your final product, you're not going to get a whole lot of X2 as a final product, okay? So you can cancel out 1. Another one that we can cancel out is actually 3. The reason is because the only way that I can form ethane here is if I have a CH3, a methyl radical, and a methyl radical colliding. Well, the chances of having methyl radicals is actually way lower than the chances of having a halogen radical. Why? Because you're forming the halogen radicals directly through my energy, through my light or my heat. Whereas these methyl radicals can only be formed after they've already reacted with a halogen. So the chances of them colliding and making a bigger hydrocarbon are actually very small compared to the chances of them colliding with another halogen. So what I would say is that I'm going to get a very tiny amount of this, like scarce. Let me try that one more time. Scarce. Wow, I'm really bad at spelling, guys. Sorry. Scarce. Okay, I would get a tiny amount of this, but it's not going to be a huge amount. Okay? It turns out that there's actually a way that we can even lower this even more. We could lower the amount of my larger alkanes that we get. And the way we could do that is just by reacting with excess halogen. Okay, if I just react with a lot of halogen and a very low quantity of alkane, then that even reduces the chances more that 2 alkane radicals are going to collide. So, depending on what my concentration is of alkane, I could basically take this down to 0. If I really wanted to, I could take this down to pretty much full 0. So we're going to cross out 1 and 3. That means that what's my real main product? Well, the real product is going to be my alkyl halide. Okay? And that's the whole point of these. Let me just move out of the way. The whole point of this reaction is that I'm taking an alkane and I'm making alkyl halides out of it. Okay? Now, the reason I taught you guys about this is because your professor is going to want to see, if you're asked to draw this mechanism, they want to see all 3 terminations. But that doesn't mean that you should draw 3 products. You should really only draw 1 major product, because that's going to be like 99.99% of it, and that's the alkyl halide. All right?